Just recently, the Meta Llama 4 model has been released, and one of its versions, the smaller version, can actually process 10 million context, 10 million tokens at once. That's its context length. And that's about 7 to 8 million words for reference, which is maybe a few books worth. I don't even know how, I can't even picture how many words that would be. Um, but it's an unbelievable amount. But previously, AI models could only process about 4 to 8,000 tokens. If you remember, in 2022, that's exactly how it worked. You had ChatGPT, the new version, and then you had Bard. It wasn't Gemini, it was Bard then. And these AI models, they could only process about 4 to 8,000 tokens. Like, what, that was the time when 32,000 tokens considered very impressive, right? Was considered very impressive. And that was like when GPT-4 was released a little bit farther away from 2022 already. So, how so? How has this happened? Today I'll tell you about what led to this massive jump in AI brain power, and I'll introduce you to the Sparse Transformer. Now, first, we must look at what AI brain power was like before the Sparse Transformer. So, you probably know already of what's called a transformer. It is the base machine learning model of all pretty much all existing AI models, and specifically of ChatGPT, like GPT 3.5, right? The very initial version in 2022. That's what it was. It was the base of that, and it was the base of Bard as well, of the Bard model. And so these were the standards. Like this was the standard for using it. You can maybe look up an image right now. I won't get that over right now, but a transformer essentially looks like this, where you have one block over here, another block over here. This is a visual diagram of a transformer. Obviously, a real transformer looks like not like the cars, the shape-shifting car, but like a set of code that's just like on a computer. And so there's like positional encodings here, there's like a process here, and then there's like multi-head attention mechanism, add a norm, and then feed forward that outputs, and then I believe it goes into here, right? And so this was the standard, the base before, right? And particularly what's important to look at in this case was how, and this is the output, right? Outputs. And there's also inputs over here. So look, this is how it looked like before. And this was the base. And particularly what's the most important thing is this multi-head attention mechanism. So this thing over here, this little block, actually represents the multi-head attention mechanism. And over here as well, MHAM, right? And this as well. So these are very special, and I'll explain to you for a moment. Just one thing I want to highlight is like specifically with GPT 3.5 and with Bard. So GPT 3.5 was only used the decoder, and I believe this is this part, and it would cut out this part over here. So it would just be this thing, right? Which looks very similar to this part, but there are like very minute differences in how they were trained and all this stuff. And Bard uses this one. Bard is based on BERT. If you have ever heard this before, you will now know what this means. Bidirectional encoder something something. Right? I don't remember what this one was. Bidirectional encoder something transformer. I think maybe is rotary or something like that, regardless. And so they just use like parts of this and like this, you know, they didn't use the entire thing. But regardless, just wanted to note that. So the most important part is the multi-head attention mechanism, which essentially, I will explain very briefly how it works. I won't explain the math, but how it works is that it has a quadratic complexity of O n squared, and I'll explain what that means. And so like essentially what it would do is when you pass in some kind of input, and we'll use the example of words. So like, how are you today? For example, something very simple. How are you today? You should remember that AI cannot understand human letters, and instead these are translated into bunch of numbers, but we won't go into that. So just know that each and every word or token is a token is a word or a subword or a phrase or something like that. So like it could be how are you, or it could just be how. Regardless, these numbers with a complexity of n squared, it means that like this is n tokens. In this case, it's 1, 2, 3, 4, let's say, n equals 4. The complexity is 16. And the reason being is because each word has to mathematically tend to each and every other word in the sequence. So this is a bunch of numbers. This token is like like they have a specific way to translate it into numbers so that the computer can understand. And so what this does is lets the algorithm know about how the word how relates to each and every other word in the sentence. So like that's important, right? You have to know if I say hello, how are you, what the meaning of are is in relation to each and every word. For a computer, that's very important. And so that's how the standard was before. That's how they would compute it. And each and every word would have to do that. So R would compute with that, would compute with that, would compute with that. And so like each and every word was calculated to be like understood in the context of the entire message. But that creates a complexity of n squared because each and every token, each and all of these n tokens have to tend to each and all of the n tokens, which is n squared. But that causes computational complexity, computational like costs, right? Computational costs. And that's the problem. That's the problem. That was the main problem with the transformer, at least in terms of its efficiency, which is now why we will go on to the sparse transformer. Now the AI brain power innovation occurs, and it's called the sparse transformer. So what do you think would be the complexity of this one? Well, it was O n square root of n. So like n times square root of n. And this, what this introduced was like, it's way more efficient, obviously. N 1.5 is obviously going to be way more efficient than n squared, right? That's n 1.5. And so how they did this was through two algorithms of fixed and sparse, or fixed and strided attention. These two different algorithms, fixed and strided attention. Now let me explain to you first fixed. We'll use an example of the quick brown fox jumped over the lazy dog. Very classic sentence, very beautiful. So there it is, there's this sentence. And so what happens is, and this is why it's called fixed attention, it fixedly divides it into blocks, right? So let's say, just for the sake of convenience, I'm sure there's a different number here, but like, okay, we can count. Oh yeah, this actually fits. Yeah, this actually fits. Okay, yeah. So n in this case, which is the number of tokens, would be 9. Now what we do is divide it into square root of n blocks. So square root of n is 3, of course, and so we divide it into blocks of 3 tokens, right? And then fox jumped over. Of course, I'm just saying tokens are words exactly, but they could be different. Like there could be a token for off, and there could be a token for er, right? So like over, like something like that, right? And there would be more tokens in that case, but we're just using this example for convenience. And so they're divided like this. And among this division, what happens is that now, instead of the word the attending to each and every single word in the sequence, it can only attend to all of this, right? It can only attend to each and every one of these. And that's it. And so this way, you have square root of n tokens attending to square root of n tokens, right? Each and every token, all of these 3 tokens, have to attend to each other. So square root of n times square root of n, right? Which is obviously n, which is 9. Okay, moving on here. That's the same thing here as well, square root of n. But we also have to see something as well, is that the word brown, it actually can also serve, and this is part of the algorithm, it can serve as a summary token. So like we can't just have these isolated blocks only pay attention to each other, and then they would not know like how the word how the phrase the quick brown relates to the fox jumped over, right? So this serves as a summary token, and it is actually computed by the word fox, right? So it kind of carries over to the word fox and is processed like that as well. So it attends to, or it is used by like the word fox, right? The word fox attends to brown despite not being in the immediate box, but it's like the last word and kind of serves as like the summarization of whatever was in here. And the authors of this algorithm actually found that it actually works well and does not like cause any issues. And so the same thing also happens here. They tend to each other, tend to each other. Obviously now with this token as well, like jump will attend there and so on. And so you have square root of n times square root of n, which is 9. So like you see that, okay, if we were to define the time complexity here, we already definitely know that there will just be a regular n here because there's a lot of these square root of n times square root of n's. And then the final part, where the actual other square root of n appears, is in that there's only 3 summary tokens. So you see, summary token number 1, summary token number 3, summary token number, or summary token number 2, summary token number 3. So 3 is square root of n. And that's where the other part comes in. So the complexity is O n square root of n, meaning that the that obviously time complexity just means like tending to how much data you tend to, right? And now that is significantly more efficient, right? It's way more efficient than, and like they've also found that there's not much like, they didn't sacrifice any quality in the text and like comprehending the text. The AI can still comprehend it correctly. So it's a massive benefit, right? You save a lot of money for it. Anyway, that's how fixed attention works. Now moving on to strided attention. Strided attention defines something differently. So if you could say previously we had like, I don't know, F, right? Or like B, right? B for box. And the box size is square root of n, right? For each like phrase box. In this case, we have S, and S is also equal to square root of n. That's where we get O's n square root of n, obviously. And so this is how it works, right? So we have square root of n, so we have n is going to be equal to 9, and square root of n is equal to 3. Then what we'll do is jump over every 3 tokens. So let's say we have the, and then 1, 2, 3, fox, and I'm just selecting them right now. You'll see what happens with the 1, 2, 3, the fox, the, right? These are the words that are going to be cared for or attended. And then we're also going to attend to the previous S tokens before that. So like that, and then well, I mean, this is not really a great example because each and every one of them gets highlighted. But essentially the point is that what you do is you first you skip over every square root of n tokens, which is 3 in this case, and you jump over like that. And you also, once you select it, go 3 position or like square root of n positions before that and select all of those tokens that you caught there. And then those are the only tokens that are attended to. Rest are completely ignored. And so this is where the n squared of n actually emerges from. Now you might actually think that, of course, it's supposed to like lose accuracy. Turns out not. They actually found that it does not. It actually instead is just more efficient and just better. And so in this context, how does O n square root of n emerge, right? If we highlight the previous square root of n tokens, we can like highlight the entire sentence. So this is a little bit, right, not a very good example. But in the case of our longer sentence, or a longer sequence of data, once you select it, so like you can imagine these are the strided tokens, and there's also like previously selected tokens, right? Everything previous to that. So there's square root of n tokens, which is 3 tokens, and each of them attend to each other. So that's square root of n times square root of n. And that is where we get the n, right? And we also attend to the previous square root of n tokens, right? Just like plain square root. And so that is exactly how we get that O n square root of n value from there. Now, okay, now that we've covered that, different types of attentions work for different things. So I believe it was that strided attention tends to work better uh, with text, or maybe the other way around. I'm not sure. But regardless, some of them is better for images, some of them are better for text. I was using the example of the quick brown fox jumped over the lazy dog in the entire time. But there are different examples, of course. So, and those examples being images and like things like that. Now, truthfully, the large and massive context window of MetaLlama 4 cannot be attributed to just the sparse transformer. There are way more things like I've heard. I don't even know how it works, but which stands for this stands for rotary. This like thing rotary positional encodings, and this is no positional encodings, right? I'm not sure how they work, but apparently they help enlarge the context window. There is something about distillation as well. And so like distillation, like this is specifically in relation to the MetaLlama 4 model. But regardless, in expanding this context window while like maintaining, even improving quality of like processing and text and like how the quality of the AI model, its performance. There's things like that I've heard, and I don't even know how they work. Flash attention, that's what I heard about. Thing like caching sequences, and even something as like seemingly illogical, like fine tuning. I'm not even sure how that could increase the context window, but regardless, it's just to show that sparse transformers were not the only thing that expanded it to this point. And there was way more things that happened. Also, there's an interesting thing called quantization. Quantitization or quantization. I'm not sure how you spell it or whatever, but it's a process of like making the model smaller by just reducing its precision, I believe. It has a bunch of numbers in its algorithm, and the point decimals to which it has those, so like 4 significant figures or 16 significant figures or 32, you can adjust that and then change its precision. I'm not sure if that's exactly what quantization is, but regardless. But that's the thing. So AI models now are becoming way more beneficial for you as a software developer, most likely, to actually be able to do code with it. So before you might have thought like sometimes I would have used like GPT 3.5 for code, or like those smaller models that whichever models they would give us, like the free versions. uh, they would not be that good in code, so they would just generate something absolutely random, like a solution to some kind of like, oh, I want this on my HTML page. It would generate some random stuff like that was completely irrelevant. Something about like maybe including some kind of JavaScript framework that's not even required. But and that's the benefit of understanding how these things work is like, okay, wow, that's why they're expanding. That's why you can fit a whole book in now. If you want, you can like somehow load up your entire project and beef it into the AI, and it will be able to process all of it. And you now know why that happened because of fixed attention and stride attention. Hey, also, if you're a solo software developer like me and you like to develop apps and side projects and whatnot, then I suggest you try Stellar AI. It's an AI tool that I made for software developers like me to be able to develop projects in a more streamlined manner. You chat with the AI and define your project goals, and you fully go step by step and like set goals, like set deadlines and plan it out, like the entire thing. If you want, you can try it out right now. Thank you.